I thank you for having me over here, all the way. This is great, and you just saw how many mathematicians it takes to get a pointer to work. So this is a talk about splines, whatever they might be, but most of you probably know what it is. Polyhedral, everyone knows a polyhedron. And then it has geometry and analysis, which is exactly the two parts that this talk has. And this is joint work with two fantastic undergrads, one of whom I just lost to Berkeley, unfortunately, but the other one I'm holding on to, and long-term collaborator Kestas Kašiauskas. So, well, you see the geometry here. Evidently, some of that pleasing looking, and of course that's what we're shooting for. And on the right-hand side, you say analysis. What analysis? It's engineering analysis. It's not analysis. So just to keep that difference in mind. This is where I'm from. And you see, this is what typically a hurricane does. The hurricane, as you can see, turns counterclockwise, mathematically correctly, in the northern hemisphere. And so it makes its major destruction, it's all in the south here. That's why you heard that they were all underwater. And then it goes 300, or almost 360 degrees to get to us, so we're safe usually. So if you want to come and visit me, it's a safe place. We never have, well, hardly ever have hurricanes that go all the way across there. Okay, so this is the story of two siblings, the B-spline form and the BB form. BB stands for Bernstein-Bézier binomial barycentric form, which was discovered by de Castelgio. He's the only one who doesn't get his name on there. So I like the BB form because it does beautiful things. We have here the discrete description of a surface through something called either control net or just coefficients. And you see how this discrete shape, this polyhedron, how it outlines the actual surface that goes with it. So you can play games that you go from smooth to and continuous to discrete and something that is computer representable, exactly representable up to floating point. And so this is a biquadratic patch, which means that you have three coefficients in each direction. That's what the bi stands for, two directions. And so 2 means that we have 3 of these guys. So, and I rendered these points that are here, I rendered them in green to give you an idea of what the structure is. And you say, of course, I've seen this before, so it's not very difficult. So a bicubic patch has 9 3 by 3 coefficients. But we can just as well, by a change of basis, represent the exact same piece of geometry. Exactly this piece of geometry. We can also represent it by the big brother of the BB form. The BB form interpolates at the corners and has this very nice, the tangent plane is already defined by the point and its neighbors. And the B-spline form is, however, preferred for other applications. And it's that kind of representation that I'm going to generalize when I talk about geometry in the first part of this talk. So these will be generalized B-splines that I'll talk about. Mathematically speaking, we have to have at least one formula in this talk. The B-spline looks like a sum over coefficients, these guys, they're gray, times some basis function, which are the B-spline basis functions, which is B stands for basis, so this is really extra B-spline basis. B-spline means basis spline. This one here, of course, is the Bernstein-Bézier form, looks exactly the same way, but obviously we have a different color. And therefore, we have these control points or coefficients and a different set of BB de Castelgio basis functions. Okay, most of you knew this already. I'm just reminding you because we're going to play back and forth between the B-spline and the Bézier form, which I brutally abbreviate as Bézier, which is really unfair to de Castelgio. Okay, we can play the same game with degree 3. Now you have 4 in a row in each direction. And again, the green is the Bernstein-Bezier form, and the gray here is the B-spline form. If you look up here, you have this polyhedral model, and I'm looking right at this place, so you can see here's the 4x4 grid, which has 3x3 facets, quadrilaterals, right? And I can now take those points here, 1, 2, 3, 4, 5, 6, 7, and so forth, 16 points, and create myself a piece of surface that fits roughly there. And if I want to, I can make a change of basis and represent it in Bezier form. Why not? And the reason people like the B-spline form is because you have the smoothness built in. And that's what we're going to do. We're going to take this here, this polyhedral outline, as our control net, polyhedral net, and it's going to automatically have built-in smoothness, just like the tensor product B-spline has. So let's look at this more closely. So we have here, that was more features than I want in one go. We have now irregular parts where we want to have a certain direction around the mouth and more of an orthogonal direction along the cheekbone. And we want to transition, and that gives rise to a point that's surrounded, in this case, by quadrilaterals. And sometimes people call them star points or irregular points. And you can also do the same thing in dual. You have a pentagon, in this case, surrounded by quadrilaterals. This is all to merge patterns. There are different patterns coming from different directions, and you sort of isotropically merge them. You don't give preference to one over the others. They're all features that you want, but you just want to blend between them. There's a second type of feature where you actually want to stop a parameter line, or you want to stop it because it's otherwise too much work to work all the detail up into this region. And so this is obviously called a T-junction. There it is, the T, right? And then you have something that's very similar, also serves the same purpose, and which is to go from some finer partition to some coarser partition. And then finally you have another type which is up here, the polar. It doesn't show very well, but I didn't want to change the view, but that's the eyes of this that you would have there, and it has this circular behavior which is different from the other two types. And so here's what you do again. You look at this as your control net, now no longer just a grid. The original B-spline tensor product had just a grid. Now instead you can have this polyhedral mesh, polyhedral net. And here's the Bernstein-Bezier form of that, but automatically put together. So just like you can convert from the B-spline to the Bernstein-Bezier form, piece by piece, this here is one spline that has as its control net this here. And then the point of the last picture is that, remember, here was the 5-sided neighborhood, and if you can't see it, then this did a good job. Yeah? So make features disappear by having good algorithms. What's underneath? Underneath is a change of variables. So again, here we have a quadratic piece, degree raised. These are all reparametrizations, the Greek letter rho for reparametrization. They're maps from R2 to R2 that take the original domain, which was a piece of R2, a square in fact, and maps it to a joint neighborhood from where we can work and transition to the outside. And so we now have, as degrees of freedom for each construction, we have these points here, the B-spline-like control points that we can move freely. But we also can play around in principle with all of these reparametrizations. Since we compose that, so we take the spline composed with the change of variables, it would be a very nonlinear problem to find both the reparametrization and the points that give you a good shape. So all these algorithms make a smart selection of the reparametrizations, and there it is. These are typical reparametrizations. It's a lot of gobbly-whoop for you just now, and I'm not going to go through the technical details. This is just change of variables with a little bit of derivatives in it. And we can, yeah?
Linear change of parametrization. The change of parametrization is linear?
No linear change of parametrization. No, non-linear. That makes it interesting. These are non-linear changes of parametrization. Yeah, so typically quadratic reparametrization in some directions, in other directions they may be just linear, and it's a mix of things. So you basically don't know this map from R2 to R2, and you make smart choices. One of my collaborators calls it math engineering, because there's a lot of trial and error involved. So let me go back one here. So there is this, so for you, what do you do with that? So I tell you there's something, I'm not even explaining to you what the math is, but there should be some take-home message. So you can click on something that you can see up there. It's called Polyhedral-net splines. It's a web page, and it has code that you can plug into something called Blender. You may have seen Suzanne before. If not, that's the name of this head up there. What you see immediately is that you have a polyhedral net. Now you can see those polar neighborhoods that are naturally for the eyes. Anything that's an umbilical up there has naturally this polar structure. And the more neighbors, the better. Most surfacing methods have trouble when there's many neighbors, but when you have a polar point, it's actually wonderful. It gets better and better the more neighbors you have. And so I can now step through with this here. I'm just going to speed this up a little bit so we don't waste our time with looking at that. So here's the control net. So you can see the control net here. This is the B-spline-like control net. And the point of doing this in Blender is, of course, that you hijack its ability to interact with it fluidly. This is the computer graphics part of the talk, where things move quickly and we get pretty pictures. Therefore, it must be good. But so this is for interactive modeling then with it. And this is an add-on that you can just download. Well, let me just skip ahead here. Here's, for example, the different patch types that were being used, the different configurations that were n-sided or were T-junctions or polar, and they're all labeled here. So a couple of disclaimers. So Blender forced us to have everything just bicubic. Even the biquadratics, we had to do something called degree raising to bicubics. So as you load this down, you just get bicubic pieces. But the nice thing is you can actually export them in industry standard format called IGES. In fact, there's another option to actually download step. So you can actually do design with it. It's slow at initialization because Blender does enormous allocations for each patch by itself. So it's just not meant. Blender has built in subdiv, which takes the whole, everyone is just happy with it until they come to the point where they have 10,000 little quad pieces to export. And that's the main difference between having finite splines versus having subdivision. There is an alternative. You can get C++ code directly by download from Transactions of Mathematical Software. Has a download site, and you can just grab it there. And again, it has export routines. By the way, I wrote this IGES export, so don't expect it to be a full. I basically grabbed an existing file, took its header, and I did all these good things that one does. And in red is the analysis add-on that I'm going to talk about in a moment, which is not yet out there acceptable. Quick primer of how you use. How do you use this? What's the input that you would give the C++ program, what's the output you get? The output is, of course, on the right. It's not a sphere. Would be horrible if it were a sphere, if everything became a sphere that you input, right? Be one way to create really smooth surfaces, but they would have no use for you. But it's this shape that you get out, and this is the input. And this should look very familiar to many of you, the OBJ file, with 8 vertices forming a cube and 6 faces telling you how to connect the vertices. So input a cube, output this here. This consists actually of 24 pieces, 3 for every vertex, in Bernstein-Bezier form of degree by 3 in each direction. And you can do more complicated objects. With that, you just saw that already. Now, why is this maybe useful for people in industry? The typical technique when you have something 5-sided like here is to take a rectangular patch and chop off one of its corners. In fact, in Rhino and similar things, you do that in 3 space. So you actually have to come up with either a surface with either a curve on the surface, or you have to find a second surface to intersect the two to actually cut that piece off. And then, of course, you start the game of having pieces cut off and other pieces to fit to that cut-off piece, which is no longer a nice piece. It's no longer in the domain straight lines. So in the end, you'll have pixel dropout, which means the surfaces that you create with this trimming process are C-1. They're not even continuous. And so this type we can get around by having these polyhedral-net splines. Here's another example of what you do with it. So you want to insert a groove, and then you get this shape that you saw on the very first slide. So what happened here is this got split and basically a cut inserted here, making this 3-sided, this 5-sided. This is the 5-sided, this is the 3-sided down there. And then there's one more refinement along here, pushed inside. And so you use the polyhedron as your modeling paradigm. That is semi-acceptable for some of the people in industry. It's not horrible, but they actually think still slightly differently. They create big pieces and cut them off, and then they spend the next 3 months to fix the cutting off. So, this is so actually finally got someone in industry to use it, a designer. He calls himself Tony Black, but he's Italian. You know him?
No, Tony is
Okay. And so he says, you know, this must be true since the designer said it's really good. So sometimes he says he actually wants to have the biquadratic and not the bicubic, because the biquadratic can't oscillate. And so for something like this robinet, you want something that goes up straight and preserves the shape. This was the comic relief between. So I'm done with the geometry now. I want to compute on that geometry. And so this is a very old idea, using splines both for geometry and analysis. I asked Carl de Boer, who has something to do with B-splines, and he said, yeah, we did something like that, but it wasn't really free-form anything. So the first paper where I saw something is Brébon and Fleury in 1983, submitted there to a journal called Computer Methods in Applied Mechanics and Engineering. And so that was in 1983. And if you look more closely at this paper, you see in there, you have something called the physical domain and the parametric domain. And same thing here. And what he's calling it an isoparametric method. But we'll have a better name for this in a moment. So then 1992, there's isoparametric spline finite strip for structures, coupling of geometric description using NURBS. And then in 2004, there's a paper that says we should use splines for both geometry and analysis. And it has a very catchy name, which from now on I will use here also, IGA, isogeometric analysis. And again, this is not mathematical analysis, it's engineering analysis. So we're talking Galerkin's method, that kind of finite elements. So what's the idea of IGA? The idea is you have one map that does the geometry. We just did that. Yeah, I'll take half as much. So we have two maps that are the geometry maps that you've just seen. And then you want to compute another map. These are these U's. For some reason, engineers use U for that, maybe unknown function. Most other people use U and V as their parameters, so that's sometimes awkward. But so here we have a function. Both are on this parametric domain, which is usually a square in our context. And so instead of having a map on this physical domain that is doing something here, we instead have a pullback to this parametric domain and then have our function that we want to compute moving forward. So we get function u composed with x inverse, which doesn't really exist. We can pull back, but its inverse doesn't exist because this is a polynomial map, and the inverse of a polynomial is just not so nice. At least you get a couple of square roots inside at the very least. And then the way, if you are into numerics, the way it only differs from the standard way of Galerkin's, this is for a second order problem, the only way it differs is that you have this term inside, which is not named after my first initial, but actually Jacobian, and it's the first fundamental form that is in there. And so going back to the example that is short and small, what you can do with that is you can compute, for example, heat. I showed you the helmet at the very beginning. The bicycle helmet that had sun shining on it. It was Florida sun, but it could have been Marseille sun. And so you have one place where heat is provided, and then there's a progression along this shape, and they should be, well, geodesic isolines, roughly equidistant. So how expensive is it to compute that? Well, you only had 8 degrees of freedom, x, y, and z, and now you have additionally a function, call it heat, or temperature, or whatever. You have a force function, and you compute that force function given that x, y, and z are given to you. So at each time step, you will invert an 8 by 8 matrix, actually a 7 by 7, because we pin down one of the degrees of freedom to provide the heat input. Which is, we're not giving the, I was cheating a little bit, I'm not giving the heat on the surface directly, but I put it in a control point. Why not? I can always figure out what the equivalent is on the surface. And so yeah, that's just, then each time I solve, I probably did this in steps of 0.01 or something like that. It's of course blindingly fast because it has only an 8 by 8 matrix. So the control net is the degrees of freedom, is the geometry, is the analysis function. And I talked to Daniele, and he said, we'll do everything with actually volumetric quadratics. And I said, well, maybe that's a little slower because you would have to triangulate, and if you go through the whole calculation of, to get the shape roughly right, even if you had a bunch of quadratic, total degree quadratic pieces, and you made this, he wants to make it a thick shell, you'd end up with roughly 43,000 degrees of freedom. So even if it's simpler degrees of freedom to some degree, it's going to be much larger, if nothing else. Okay, so same thing here, same idea, heat structure. And now my two fantastic undergraduates, we shouldn't let them graduate. The good ones we should keep forever, and the rest we should graduate very fast. So they built this wonderful interface, which, make this large here a little bit. There we go. So everything, so they had to present it, so like a final capstone project. And so they made it overly pretty. I just wanted the raw numerics happening and things showing, but they actually created an interface, which is out there. We can sit down and look at it afterwards, which has examples in it. I forced them to put them in there because they said it's obvious, and then okay, it's not obvious to me. Let's slowly go and put some things in, and so you can specify boundary conditions like von Neumann, Dirichlet boundary conditions, and yeah, in the end you get various different shapes. We have a cylinder with boundaries. That's when it gets interesting, when you have boundary conditions. Or, yeah, here's something that is like a disc shape. Many of these examples were used just to be sure that we can actually compute exactly with this. And this allows me to finish on time.
Isogeometric analysis is not so much used in the industry.
Oh, why is isogeometric? The first thing is, since you were in industry, you'd probably agree, is a certain conservatism.
Yes, I agree. I agree.
The second thing is, of course, that what isogeometric analysis was trying to do is to force people to use their approach to modeling, and that didn't happen. So once they have trimmed patches, it doesn't really work so well, because now you have integrals that are over restricted domains with difficult curves in the domain. Of course, you can approximate it, but then you're back in the game of approximating. So why not approximate with lots of small quadratic pieces or something like that? So the difficulty, so if indeed you have a design that has been done right in the beginning with isogeometric analysis in mind, then it's just on the dot. Like they did in the previous millennium. I showed you all these examples. Perfect. Yeah? They knew what they were doing, and they did it right and higher order. And so the idea here is to try to ease them over, but whether this ever gets into practical use, we'll see. I've been trying.
This has been used actually in industry in recent years. I mean, ANSYS, for instance, bought a American company that was trying to do this IGA computations.
Oh.
But again, they were
what's the company's name?
I don't remember, but I can ask the ANSYS people, because they
Okay,
acquired the company, and now they're trying slowly to
But
use
not
them.
core form.
Well, they realized that there's problem with all the trimmed.
Oh, yeah.
So at the end of the day, who knows what's going to happen? But because it was Hughes that proposed the IGA, people listened. So this is a typical example where a big name sort of forced the companies to think about it. Whether it's going to work out at the end, that's unclear.
Yeah, so I should probably mention the big difference between the early work and then what's later is being able to do something without trimming. All the early work required trimming, all the IGA. And the idea is, how do you get over it? You can either use something like subdivision, which some of us have worked on, right? Many of us have worked on. And that's one way to get over it. Or you use these polyhedral-net splines, which have the advantage that you have just a few finite polynomial pieces, and so integration is not a problem. But getting people to use it one way or the other, designers, that's the hard part. So if one can get the designers to use something like polyhedral-net splines, then you get for free your analysis at the back end.
Change all the process.
Yes.
No, you don't change the process. You simply add on to the existing B-spline representation. You add on these extra configurations, and then everything stays the same.
No, but you change the design process. You have to use.
Also not really. What you want to do is, so it doesn't replace all trimming. There is a type of trimming that you cannot avoid. Two surfaces intersect. There is a type of trimming that you can avoid, namely getting n-sided patches by restricting the domain. That is unnecessary to my mind. And then there's one in between where you have a large surface that has been beautifully designed, and you want to just carve your initials into it at 2 orders of magnitude smaller. I think there's something to be done where you actually want to facilitate trimming in the right way so that you don't have any errors. But that's next time.
Since you're one of the very few experts that know splines and subdivision surfaces equally well, is there anything that you could say that would recommend either the spline version, the Polyhedral-net splines version, or the subdivision surface version for a given application?
Oh, so now I'm supposed to decide between two kids. Well, they each serve, I mean, subdivision is beautiful. You apply a matrix to an existing grid and you get the next finer grid. So in particular, if your goal is just a refinement of what you have and not the limit surface, then for sure you want to go with some subdivision algorithm. What I actually like very much is the hybrid between these two. You can actually do a couple of steps of subdivision followed by putting a cap in the rest. You have to be careful with the cap so you don't get the big dent in there. But no, I'm going to be quite neutral between the two kids there.
Thank you. I have a last question. So usually when we had talks on curves, we asked about surfaces, but you have the surfaces. What about volumes, if you want IGA?
Yeah, that would be a different talk, but no, there exists. So a paper was submitted some couple of years ago to a journal called CMAME that solved the problem using C1 tricubics of computing things like fourth order equations. And it came back with the mention, we're not interested in this topic. That paper was then subsequently submitted to a much less interesting venue because my student wanted to graduate. And so yes, we can do things. This kind of construction here in 3 variables is very hard. There you can do subdivision is one thing. Interesting things happen there, namely things that ought to be 3-dimensionals collapse because your eigenvalues are not the same. And you can also use singular constructions, which is the one that gave you a tricubic hex element. And that actually works.
Okay. Thank you again.
Thank you.